Hi everyone, today I'm going to be speaking to you about rapid prototyping, which is a really important term for you to know, something that is having a big impact on manufacturing, and we also use it quite a lot in school. So we are going to have a chat through what it means, the benefits of it, and it's quite a common question that comes up in the exam, so definitely one to get your head around. So, designers and engineers, they use rapid prototyping to create representative prototype parts. So parts that actually look like the final product that you're trying to create. So there's reasons they do this. They do this to aid the visualization of the design, so that you can actually visualize it and see it in real life. So obviously there is benefits with CAD to do that. You can see it in 3D on CAD, but nothing beats actually holding and looking at something in real life. But also, creating a real prototype of the product can massively help in the development of the manufacturing process before you take it into mass production. So you can iron out any little flaws, any changes that need to be made to the shape so that different manufacturing processes will actually work, such as injection molding and blow molding and rotational molding, all those different types of things. So there are different types of prototypes. This is just something I found online and I thought it was really interesting. And this is obviously a Dyson example here. But you categorize prototypes in different ways. So low fidelity prototypes, kind of like this one and this one, though I would argue that these are still very well-made prototypes. They're very simple, they're quite quick to produce, and they're kind of testing the broader concept. So we do loads of this in A-level product design. You make a card or a styrofoam model to really quickly test the idea to get you thinking about it. Then you have something called high fidelity prototypes. And these are ones that actually appear and function quite closely to the final product. So they might have some working parts in them. So for example, on this vacuum cleaner, maybe the button might function. Where this connects in here might function. You can see that the kind of engine little bit in there looks like it could potentially function. But a high fidelity prototype is much closer to what the final product might look like, and it also might function. So this is where rapid prototyping comes in, because it allows you to produce more high fidelity prototypes. So how is rapid prototyping actually done? Well, it uses something called additive manufacturing. Okay, so whereas more traditional manufacturing methods kind of subtract material, so for example with a router or a drill, you've got your block of wood or metal and you drill into it and you remove material from it. Well, these rapid prototyping processes, they add material layer by layer. So there are lots of different methods of rapid prototyping, but obviously that might kind of confuse you slightly. So the two that I'm focusing on are kind of the two most common and ones that have really kind of taken off in the last 10 to 20 years. So the two that I'm focusing on in this video are fused deposition modeling, which you might be like, huh, what? That's 3D printing. That's what we do at school. That's basically, the plastic goes in and heats it up almost like a glue gun and creates layers of plastic. So that's adding different layers. And then there's this one, direct metal laser sintering, which sounds more confusing, but this is basically metal 3D printing. And I'll explain a little bit more about how this works later, but this is basically like a powder that is melted in certain spots with a laser. So these are the two different types of rapid prototyping processes we're going to kind of focus on in this video. The first one I'm going to look at in a bit more detail is the fused deposition modeling. So this is the one that we have at school. So we've got about 12 of these pieces of kit, and there's a big advantage of these is that they are quite low cost. They are quite easy to, you can have them at home, you can get them lots of different sizes, They print in a variety of different materials. So basically it melts and it extrudes the thermoplastic onto a platform layer by layer, and you create your part. So you can print in lots of different polymers, and they can produce relatively sturdy, usable parts. So, you know, we've all 3D printed things at school, and they are, depending on how you print them, they can be quite strong. Now, the advantages of this process, just generally speaking, it's quite a cheap additive manufacturing process. So here it says compared to SLA, that's called stereolithography. Now that is basically a resin printer that I have in my office at school, and that uses UV light to cure layers of kind of resin. That's quite expensive. The one that I've got in my office was quite expensive and tricky to use as well. And SLS is another type of laser sintering, which is slightly more expensive. So this is on the cheaper end, or the more inexpensive end, I should say, of additive manufacturing. You can make complex parts because of the supports that can be put in place. And you can use a lot of different types of thermoplastic. So you can use ABS, you can use PLA like we use, you can use polycarbonate, you can use lots of different types of thermoplastic, so it's quite flexible. There are some disadvantages. You get sometimes a good surface finish depending on how well calibrated you've got your machine, but you do get this kind of ripple effect. You can kind of see it in the layers of the print. This can be a big issue, especially if you need your part to be strong in a particular direction. So for example, if you've got a part like this that has got prints and it's almost like the grain in wood, if you were to put any force on here, for example, it could quite easily snap along the weak area. So it's got low strength in the Z axis, so going up and down the height of it. Depending on which way it's orientated, it's going to be slightly weaker. It'd be more likely to crack across there. So therefore, it's got quite limited suitability for actually testing the product. So if you were 3D printing a functional part, it's not going to give you a realistic representation of something that might be injection molded, because an injection molded part would be much stronger in lots of different directions, because obviously the plastic is fully melted down, flows around the mold, and it doesn't have any particular structure inside. So that's fused deposition modelling. That's the ones we have at school. So I'm going to write school on there. Okay, so get used to that. If you saw that come up in the exam, you'd probably be like, huh, what? But it's just the normal, I say normal, the more common additive manufacturing process, 3D printing. That's what you think of, fused deposition modelling. Right, this one is a little bit more expensive and is very common. It's commonly used in kind of more intricate metal parts. So this is kind of like metal 3D printing. So lots of people kind of think, well, how do you 3D print in metal? Do you have to heat the metal up and then it melts? Imagine the temperatures that you would need if you tried to do fused deposition modeling with metal. It just wouldn't work. So the way that this is done, and I'm going to put a video linked under this one. So have a look on the VLE if you've got this off the VLE, or go onto YouTube and type in direct metal laser sintering if you just don't get this process. But this works by melting and fusing layers of metallic powder. So this could be titanium, it could be stainless steel, it could be cobalt, it could be lots of different types of metals, different alloys. And basically what is done is, if you imagine this is kind of like the base of the 3D printer, there is a layer of powder, this metallic powder, and you can see that on this image here being brushed away. And every time when the model is sliced into its different layers, so each layer will have different shapes that it needs to print on top of each other, it uses a laser beam just to, if I use a different colour here, it uses a laser beam just to fuse and melt certain parts into the powder. Okay, then what happens is another layer of powder is brushed over the top, and then the laser goes again and it melts again on top. So it's kind of building those layers up. So it's kind of quite a bit different to how FDM works, but I hope that kind of makes sense. So the big advantage of this is it can produce really high quality metal parts, really complex parts, and it makes parts that would be extremely difficult to make using more conventional CNC machining. So even if you had a 5-axis CNC router with, you know, your piece of metal on here, and this is spinning, by the way, and this is turning and spinning, it would be very difficult to make something like this because of all the gaps and the hollows and the cavities. So the big advantage of this process is it can make really complex parts, and they are full strength. So it doesn't mean that it has any weaknesses in any area. It basically comes out as strong and as functional as the final mass-produced part would. Okay, so you get excellent material properties, and you can use a variety of metal alloys. As long as it melts under this laser beam, then it'll work. Now you're probably thinking, well, why don't we use this for mass manufacture? Well, this is the issue. It's very expensive and it's extremely slow. So you can see that actually die casting this, high pressure die casting, would be a better option for mass production, or investment casting would be better. But you can see that you might use this process to prototype and to produce a one-off to see what the product might look like. So that's what this is. I hope that makes sense. If you really don't get it, let me know, or have a look on YouTube and see if you can find some videos to explain this process. So direct metal laser sintering is the other additive manufacturing process I want you to know. Now we're going to talk through some advantages of rapid prototyping. I'm going to go quite quick through this because I got some of this online, and it's some of it, I can already see a Z there. You can see it's very Americanized. But it was a really useful website because it picked out lots of the main kind of advantages of rapid prototyping. So the first one being, number one, is you can prove your concept. You can prove your concept works. So beforehand, designers, engineers had to rely on virtual simulations, CAD, but now they can use one of these additive manufacturing processes to produce a very near accurate copy of what the final product might look like. So obviously that is going to reassure your clients. You might get investment based on a rapid prototype of the product. On Dragon's Den, a lot of those prototypes will have been rapidly produced using FDM or using direct metal laser sintering. And they can be tested in real world situations. So you can actually grab your prototype and test it, try it out, see if it works. All of this being done at a low cost because you're not having to pay for molds and expensive tooling that would take a long time. As well as that, because you can do this quite quickly, so your product could be printed in a manner, in a number of days. You could repair it, you could optimize it, you could change it to make sure that it is mechanically sound. I like that, mechanically sound, before you send it off to be mass produced. So you've eradicated any problems with it before you send it off to be produced. Okay, so that's a big advantage of rapid prototyping. Second one, it's a really fast turnaround time. So I spoke about that a little bit on the previous slide. You can really quickly create your design, and then if there's an issue with it, you could send it back, send the CAD file back, make a slight change, slight tweak, and get another copy of it made really quickly again. And doing that, you're going to save on labour, production costs in the future, because having prototypes made previously relied on really highly skilled model makers to do it, cost a fortune and took a huge amount of time. So this gives a fast turnaround time on this part of the design process. Another one, additive manufacturing actually allows you to manufacture really, really complex parts. So for example, we were talking about the direct metal laser sintering. You can produce those really complex metal parts without having to change them or be limited by traditional manufacturing. So if you were doing a short run, you might use direct metal laser sintering as your manufacturing process. If you are mass producing complex parts, you will use this process, direct metal laser sintering, to help you work out how to optimize the design so that it can be more easily made in traditional manufacturing processes. So it allows you to be a lot more creative, definitely, and you're not quite so limited, not limited by a process. You know, you don't have to think, well, I need to injection mold this part, so I need to have split line here, and I need to have this here and this here, and where's the split, you know, where's the parting line going to be, and the injection pins and all that. This gives you a little bit more freedom. This one here, it reduces material cost. So CNC, like I spoke about earlier, you would have a big block of material, and this CNC milling machine would get rid of all of that material, and you can see it all flying away, and that's all waste. You can't really do much with that, and that's more traditional here. So using a subtractive manufacturing process. But the additive manufacturing, because it's just adding layers, it's not getting rid of anything, you have less waste. So you might have some support, you know, but you don't have as much waste as more traditional manufacturing processes. So it ends up saving on material costs and eliminates the kind of unnecessary waste. So it's good for your lean. It's good for your lean manufacturing. Let's put that in there. Definitely. Another big advantage, I can't remember if I'm on 4 or 5 now, but I'm going to put 5. You can easily customize things. So if you are a small company, you could easily customize parts to fit onto an existing design. You might want to add some personalization into your design, and that's where rapid prototyping kind of comes into its own. Whereas injection molding, you would really struggle to do that. With rapid prototyping, you can do that easily. But 3D printing is not yet able to match the large volume capabilities of more traditional methods. So it can't match injection molding or die casting or anything like that. But if it's for a small run, a small amount of products, then that's where rapid prototyping and additive manufacturing would be really beneficial. This one's pretty obvious. When you use rapid manufacturing, you can produce prototypes to identify any potential flaws or weak points in the physical model before sending it off for mass production. This is a massive advantage. You know, if you use the direct metal laser sintering, and I keep saying that to get it into your head a little bit, you're going to make a metal part that's very similar to the final product. And if you are able to test that and see that there are some weaknesses, you can get rid of that flaw before it is put into your final product. So that's going to save a huge amount of money in the long run. If you think about how much that would cost to then fix that problem after the product's been made, it'd be quite devastating to the company. So we've gone over the advantages now. There is another really interesting way that rapid prototyping is being used in manufacturing. This links to another topic that comes up a lot in A-level product design, which is the use of production aids, jigs, fixtures, things like that. Quite often now companies are using 3D printing to make things like manufacturing jigs or fixtures to help with the manufacturing process. So this is called rapid tooling, which is really interesting actually, because if we take this example here, this is a 3D printed fixture. Now, if you can't remember fixtures, fixtures are basically a device that holds a component in part when it's being processed, when it's being drilled or cut, or something is happening to that component. And I've shown you examples before about car doors and things like that, about how difficult they would be to support. And if you don't have a fixture, what can happen is it can slip, it can be, the part can be ruined, and that would cost a lot of money. So 3D printing has really helped with this, because these fixtures can be really expensive to produce because they're all custom depending on what part you're working on. But being able to 3D print your own fixture is going to save a huge amount of money. And quite often the company who are maybe producing these parts, they might have their own 3D printer, so they can 3D print their own fixtures. Going to massively help with things like your quality assurance and quality control. Okay, so that's an example of a fixture. The one that we were just talking about here, and so is this one. So you can see that this looks like an injection molded part that is being supported in a 3D printed fixture, and that's custom made to suit the needs of that product and that client. Really like this one as well, and you find loads of these online. This is a 3D printed jig which you can slide your product into, and you can line up and drill a hole in a particular place. So again, another really good example of how 3D printing can be used to aid more kind of traditional manufacturing methods, bringing that kind of more modern edge in to improve things like quality and accuracy, and therefore reducing costs. So reducing costs and upping speed. Right, in conclusion, rapid prototyping, there's the two main ones that you need to know. So don't forget your FDM, your fused deposition modelling. Don't forget your direct metal laser sintering. Don't forget that they are additive. They are ideal for prototyping, small run productions, or customizable components. You can save a lot of money and time by iterating design. So don't forget, iterative design means making lots and lots and lots of versions to make sure that it's going to be a good, a well-finished, functional product. Get rid of any flaws, make sure it meets the specification. And this is really important. It enables a faster and more affordable path to mass production, because you are going to be able to plan and see what the problems are and tailor that product to be able to be made in mass production. So you would go from a rapid prototype, an FDM prototype, to an injection molded final product. At the moment, traditional manufacturing is still advantageous when it comes to making products in larger volumes. So you can see that here. The price per part, depending on the number of parts, so say this is obviously on the higher end, you can see this is just in terms of money. You can see it's lower. But at the beginning, you have the big advantage that 3D printing is much cheaper and conventional manufacturing has a much higher startup cost. So this is only focusing on the money, but actually the other issue is time. And additive manufacturing at the moment can't compete with traditional manufacturing on the speed of how quickly the parts can be made. But the gap between these two different types of manufacturing are closing quite quickly. So I think in the future, we will move more towards rapid prototyping and additive manufacturing methods. Right, I hope that was useful. See you on the next video.